So hopefully we'll be able to do some calculus today, and people will pay attention to it, because what I noticed with my linear algebra class is that nothing that we've done in the last week has actually solidified into anyone's mind. So do you guys remember what we've done here for the last week? Implicit differentiation was 2 weeks ago. Do you guys remember the whole mean value theorem digression? A little bit? Okay. Rolls theorem, good. Okay. Better than I expected. All right. Let's take all of this and do just one last bit of really important theory. Let's actually connect everything. So if it's called the fundamental theorem of title of the course, what does that mean? Means it's on the exam. Means it's on the test. Yeah, absolutely right. Good. So important stuff. What this is going to do is it's going to link two ideas that have seemed like they're somewhat related. We have looked at anti-differentiation. We have looked at the area under the curve. And the answers that we get for one seem to be fairly similar to the answer we get for the other. So this is the thing that's actually going to join them together and show that they really are the answer to the exact same question. Right, what we're going to do is we're going to begin with a continuous function. And let's have it continuous on the entire interval from A to B. The fundamental theorem has two parts. Really, it's two directions. We're going to show that the derivatives are the inverse of integrals, and we're going to show that the integrals are the inverse of the derivatives, roughly. Right? So in a very general sense, that's what we're going to do. We're going to claim that the derivative, the derivative with respect to x of the integral from a to x of f of t dt is equal to f of x. Okay? So that's a fairly wild claim, because what it says is that the area function, right, and here we're going to use this as the area function, as the limit of the Riemann sum for the area under the graph. We're going to show that that has a derivative equal to f of x, which means that the function itself, the integral, is an antiderivative of the function f of x. And so if we can find an easy way to figure out the antiderivative, that's good enough. That'll show us everything that we need to find. Right, so all we need to do is prove this. And we can't get away with just, well, trust us. Right? This is the fundamental theorem. You want to have a proof of it if it's at all possible. So first of all, let's look at the function itself. We have our grid over here. This is not the x and y axes. This one's t, this one is y. Okay, t is just, I need a throwaway variable. I need a variable that is not x. So I can name it whatever I want to name it. T is just the standard. And we're going to start at some point A, and we're going to go up to some point x. And this bit over here, that's the function. That's the value of the function, the area under that region. And we are going to try to find the derivative of this thing over here. So you look at it, you stare at it for a while, and hopefully everyone over here has the same reaction, which is, I've got no idea what the first step would be. But if we don't know what it is, then we've already talked about this. You unravel the definitions bit by bit. I don't know what the derivative of an integral is, but I know what a derivative is. I know what is the limit definition of a derivative. I've got absolutely nothing else that will apply over here. Fantastic. That means that's the correct first step. So this is the limit as h goes to 0 of the integral from a to x plus h of f of t dt minus the integral from a to x of f of t dt, all divided by h. Right? The area up to x plus h minus the area up to x, all divided by h. I am using the definition of a derivative over here. Nothing else. Right? No trickery. But since the function is continuous, since it's continuous, then taking this minus that means that I have one area minus another area, and so I can rewrite this as the integral from x to x plus h of f of t dt. Okay? Right, area from a to b minus area from b to c. Well, from a to c. So let's rewrite it. It's the limit as h goes to 0 of 1 over h times the integral from x to x plus h of f of t dt. So what we have is that there is a very small rectangle over here from x to x plus h. Well, it's not exactly a rectangle. 3 of the sides fit perfectly well, but that top side looks a little bit different. It's a decent approximation, though. Okay, as a matter of fact, we can use the intermediate value theorem to talk about how at some point between x and x plus h, there is a height, there's a particular value for my x coordinate where at that height, I'm going to get exactly the value for the area under the graph. Okay, so let's come close to proving that. We're not going to do it perfectly, but we're going to get a sense of it. In our example, our function is increasing from x all the way up to x plus h. All right, so if the function is nice, then the integral from x to x plus h of f of t dt is between a pair of values. It's between f of x times h and f of x plus h times h. Okay, so what do I mean by nice? In this case, I mean it's always increasing in that interval or always decreasing. Okay, if I don't have that, there's actually some slightly more powerful mathematics that allows me to come up with something close to that. Okay, so we're going to prove this at our level, but we're going to prove it well at our level. There is a higher level. If you're really interested in it, you can go across the street and you can take MAT187. They haven't gotten to this material yet, and you can see how they prove it. It's really, really cool stuff. But it's detailed. Like they prove it for anything. So by the intermediate value, by the IVT, there is some point C in the interval between x and x plus h such that the integral from x to x plus h of f of t dt is equal to f of c times h. Right, the rectangle on the left is too small, the rectangle on the right is too big. Somewhere in the middle, is a Goldilocks type of rectangle. It will give us exactly the same as the area. But what that means is that this thing over here, so the derivative of the integral from a to x of f of t dt, is equal to the limit as h goes to 0 of 1 over h times f of c times h. And the h's are going to cancel out. As h goes to 0, what happens? C is stuck between f of x and f of x plus h. And h is getting smaller and smaller and smaller. So what we have is, about the only good scene from the entire Star Wars trilogy, where you've got the room closing in on everyone as they're trying to find their way out of it. Right? That's what it is. It's coming down, it's squeezing, so we are actually able to use the squeeze theorem. It's squeezing the value of C itself, and you're going to end up with C has to go to X. Right, so this is because C is between X and X plus H. As H goes to 0, this guy stays, this guy goes to X. So the limit of f of c has to be equal to f of x. Okay, any questions about this? Yeah?
Can we go back to the first line? Just
Sure.
under where that graph is. I'm still not clear as to how we got from the first line.
From the first part, from the left side to the right side? Yeah, so all I'm doing is I'm applying the definition of a derivative. Right, so it's the limit as h goes to 0 of the function at x plus h minus the function at x, all divided by h. But where am I putting my variable? My variable is the top bit. Right? It's the upper bound. So I'm going to bring this back up in a second. Right? My variable is the upper bound of the integral. So if I have this function at x plus h, that means over here I'm putting an x plus h. And when it's x, it's just x. And so I've got this guy minus that guy, all divided by h. So I'm just using the definition of a derivative. I'm not looking at the definition of the integral, just the definition of the derivative.
And then how do we get to simplify that to just the integral of x to h?
So to simplify it, I have one, let's really exaggerate the distance between x and x plus h. My first one is I'm going to take the area from A all the way up to x plus h. But then I remove from it the area from A to x. So everything that's cross-hatched, you've got positive minus the same thing. So it cancels out. And it leaves me with exactly what I'm looking for. Okay? Yeah. Her first and then you. Yeah.
So if it's not like smaller than or equal to, how can you apply the squeeze?
For the squeeze theorem, we don't actually need equality until we take the limit. So you can have the one thing less than the other. So if you remember the motorcycle, that gruesome motorcycle example that I came up with, it's the idea of if the motorcycle never actually touches either one of the trucks, it can keep doing that for a very, very long time, right? And the trucks aren't touching each other until we get to the limit. Right? So that's what happens over here. We can have them be strict inequalities, but as long as the limits are equal, the squeeze theorem still holds. Yeah.
Can you explain again why we use the intermediate value?
So the idea for the intermediate value theorem over here is if I look, let's use the diagram over here because this one's nice. Let me clean this up a little bit. So my function over here, my function f is increasing. So if I took a single left-handed rectangle, then the area of that rectangle is less than the integral. It's less than the area under the graph. If I used the right-hand endpoint, this area is bigger than the area under the graph. So because my function is continuous, somewhere inside, there's got to be a point that's exactly equal. Okay, so in the high-level mathematics, we have to be a little more precise about this, but the idea holds. It's very much the same idea. They just don't use left hand, right hand. They use lowest point, highest point. Okay. Anything else?
Explain one more time, like how is the limit of fx and fx the same, so that you can use this?
Not the limit of fx and f. You mean this bit over here? What's happening is as h goes to 0, x itself is not going to change. It's just going to go to x. X plus h is also going to x, because h is going to 0. So they're both going to the same point. And therefore, this value c has to follow with them.
Oh, so the limit of x and the limit of x plus h each other, so you could say limit of
Exactly, exactly. My function is continuous. Since it's continuous, I can bring the limit inside. No problem. Okay? Anything else? Right, this is important. If you understand it, it makes this course easier. So any questions? We can take as long on this as you guys want, because I want to make sure that everyone has some, it doesn't have to be a perfect understanding of it, not right away. I didn't fully understand this until the exam for my calculus course in first year. It was during the exam when I suddenly figured out what the whole thing was and how to apply it and everything. Not a great time to figure it out, but way better than 2 hours later. So it's something. I was able to get the marks. Yeah.
Can you explain the part that's like above identity? Like that was something else.
This bit here? So that's what I was drawing over there in terms of the rectangles. Right? One of them is going to be too low, one of them is going to be too high. And that's the idea over here for the function being nice. If it's always increasing in that interval, or if it's always decreasing in that interval, then this conclusion is correct. Okay? And if it's not, if we have something where the function goes up and comes back down, just take a smaller value for h. Right? Just keep cutting it smaller until you have something where the function just increases or just decreases over the interval. And then you've got one that's too small, one that's too big. The exact value is somewhere in the middle. And then the squeeze theorem gets everything. So notice what we're using over here is definition of derivative, definition of integral, the intermediate value theorem, the squeeze theorem. This is like 3/4 of the theoretical stuff that we have done in this course all comes together. And all of it to show that the two major ideas that we have defined using limits are actually very, very intricately connected. Okay, anything else? Good? All right. So this has a number of fairly interesting applications. One of the most important ones for students, because we always ask questions about this on the test, is that we can take the derivatives of functions in general. Okay, so we will use this to be able to find the derivative of the integral of any kind of bizarre thing without having to take the intermediate step. We don't have to find the integral when we're just going to take the derivative of it anyway. So we'll put that together. But first, let's add the other part of the theorem. So I'm going to leave this bit on the board. And I'm going to add to this so this is the second part of the fundamental theorem of calculus. There isn't a formal numbering. There isn't this one's the first part, this one's the second part, and it's the same way in every last textbook. You choose which one you want to prove, that's part one. And then you use that result to prove the second one, that's part two. So there's no canonical way to do it. So part two, if big F of x is an antiderivative, which is to say any antiderivative of little f of x, then the integral from a to b of f of x dx, or if you'd rather write it as f of t dt, that way it looks a little bit closer to what we have on the left-hand side, that's fine too. At this point, it's just a dummy variable. This is equal to big F of b minus big F of a. Okay? So, how do we go about proving this guy? Well, what we're going to do is we're going to take that thing over there, and we're going to use what we have over here, and we're going to also combine the one thing that we had in terms of theory that we haven't used yet today, which is the mean value theorem. So that way we get to put the entire course on here all at one shot, which is really nice. Okay, so we know that the derivative with respect to x of the integral from a to x of f of t dt is equal to f of x. We also know that since big F is an antiderivative, then its derivative is equal to f of x. Let me get rid of the prime notation and use the Leibniz notation. That way you can see I'm taking the derivative of one function and getting some value. I'm taking the derivative of another function and getting the exact same value. And what did we show with the mean value theorem? That if two functions have the same derivative, then they differ by a constant. Okay, so these are equal. So, by the mean value theorem, big F of x is equal to the integral from a to x of f of t dt plus some constant c. Okay. Which means that we can go over here and actually prove the entire thing very quickly. Right? Because what do we have on the, let's begin with the right-hand side. Okay, the right-hand side is equal to big F of b minus big F of a, which is equal to, by what we just showed, it's the integral from a to b of f of t dt plus some constant minus the integral from a to a of f of t dt plus the same constant. Right? It's the same function. I haven't changed it. I haven't played with it. So these plus c's, they're going to cancel out. What's the integral from a to a? It's 0, yeah. Right? What's the area of a line? Not very much. So this guy over here is equal to 0. So this is the integral from a to b of f of t dt. And does it matter whether I label my axis t or x or smiley face or whatever version you want to use? It doesn't matter. It's just the name of the axis. That doesn't change anything, so I can go back over here and just write it as f of x dx. So that gives us both sides of this. Okay? Yeah?
I'm just trying to see if I understand. So basically, using the fundamental theorem practice, you're just saying that if two functions have the same integral, then it means that they differ by a constant?
So first of all, using the mean value theorem, if the derivative is the same, then the original functions are different by a constant, right? Yeah, so what we had shown, the original corollary that we showed is that if a function has a derivative that's always equal to 0, then the function is constant. So when we have two functions with the same derivative, we can just look at function 1 minus function 2. Its derivative has to be equal to 0, right? Because it's the derivative minus itself. And so the difference between the functions is a constant. So yeah, it's a nice one. It should be somewhere in your notes. I understand over the last week you were focused on a different course. It's all right. As long as you've got this stuff. Right, for next week, we'll really get your attention. We'll take all of this. We'll look at some of the applications of a bunch of the material that we're looking at. We're going to look at max-min questions. We will use max-min questions to prove that baseball is not a sport. We'll do a whole bunch of really interesting things. So there'll be some really cool stuff. Okay, so far so good? Reasonable, we'll accept it? Okay. So let's play around with applications. The applications of the second part, or what we're calling the second part, they're so common, so frequent, that you're very quickly going to stop thinking of them as applications of the fundamental theorem. They'll just become what you do. So if we wanted to take the integral of, say, 2x dx, but not as the indefinite integral, not as the area under the graph in an unknown way, not as the antiderivative, but specifically from, I don't know, let's go from 1 to 3. Okay, this right here, this is area under the graph. We should do this by Riemann sums. We should figure out, okay, so we're going to take the interval from 1 to 3, and we're going to break it up into n little pieces, and we're going to figure out what is the area, well, what is the height for the function at each of the xi's, and about an hour and a half later, we're done. But the antiderivative of 2x is x squared. So all I need to do is take the function x squared at the point 3 and at the point 1, and I'm going to subtract 1 from the other. The notation that we use, so we put a line over here from 1 to 3. Not a bad idea to write over here as x goes from 1 to 3. It will help you when you get to Calc 3. It's not necessary. So I don't tend to do this because I don't teach Calc 3. I teach Math 290, which involves some other stuff. But it's entirely your choice. So that notation means first I plug in the top bound, and then I plug in the bottom bound, and I subtract the one from the other. And so this is equal to 8. And if we went through the Riemann sums over here, we better end up at 8 for our area. Okay, and we can go through it, and it works out. If you've got, a half hour to kill, we can run through it quickly, but we've only got about 20 minutes. All right? We can play around with this with any function. Right? You can make the functions difficult. If we had x, better yet, let's just go with a simple trig one. If we had the integral of sine of 3x dx from 0 to pi. Riemann sums are very difficult over here. Right? To do Riemann sums, you're going to end up with the sum of n different sines. Right? Sine of x1, sine of x2, sine of x3, and you need to figure out what happens when you add all of them together. That's not easy. It's not impossible. This function is nice enough that we can do it, but it is very straightforward to come up with ones where we can't, and things blow up. So Instead, we look at this and we think about the antiderivative. What is the function whose derivative is equal to sine of 3x? You could see them writing it down while I was calculating. Good, right? Negative 1 over 3 cosine of 3x. And we're just evaluating it from 0 to pi. And that's it. Plug in the two values, subtract the one from the other. Negative cosine of 3 pi over 3 minus negative cosine of 0 over 3. Probably be nice to get rid of these guys. Then what do we have? Cosine of 3 pi. If you don't remember, you go to the unit circle. 1 pi, 2 pi, 3 pi puts us over here. Cosine is the x-coordinate, is equal to negative 1. So this is equal to negative negative is positive 1 over 3 plus 1 over 3. Total area is just 2/3. Notice at no point did we even write down by the fundamental theorem of calculus. Okay, it's something that we use so many times, you run with it. It becomes second nature. That's perfectly fine. Okay? Other questions? We're good? Excellent. All right. Where things get interesting is if we have something like the derivative from, say, 3 to x squared minus 4x of sine of t squared dt. We'll always put in something like sine of t squared, e to the t squared, something like that. Just in order to point out, you want to figure out the antiderivative of this guy, go right ahead. It will take you an infinite number of functions. So, good luck. We'll see you at the end of the universe, and we'll see how far you've gotten. Sometimes we won't do that. Sometimes we'll put in something that you can integrate, that you can figure out the antiderivative. But we'll just make it something where it will take you a lot longer. Okay? If you are asked for the derivative of an integral, use the fundamental theorem. It will necessarily be the quickest way through this particular problem. But this over here and this over here do not match up. One's an x squared minus 4x. So what do? Chain rule. That's it. This entire application is nothing but chain rule. The derivative of the integral from 3 to x squared minus 4x of sine of t squared dt with respect to x squared minus 4x times the derivative of x squared minus 4x with respect to x. This is equal to sine at x squared minus 4x squared. Right? My variable t, I just plug in whatever the upper bound is, whatever is my variable for the top end, times 2x minus 4. Right? So we thought we were done with the chain rule. We had used it in so many different applications, and here it is showing up again. In order to use the fundamental theorem of calculus for this particular application, for the derivative of an integral, all you have to do is use the chain rule. As a matter of fact, we can go at a fairly high level with this. So what we can do is we can look at the questions in general, and within mathematics, there is this piece of terminology which is really effective. It's called abuse of notation. It's what happens when you take a piece of notation and you use it improperly, but with a sense that most people will understand. This is not allowed on a test, but it is allowed when you're proving some things, between friends. Okay, so we'll figure things out, but first, yes? Sure, sure. So just going over it one more time. You know what? Let me do what I'm about to, and hopefully at the end of it you'll have a better sense of where this guy comes from, and I'll be more than glad to go over it again at that point. Okay? So let's take that integral from a to x of f of t dt. Let's refer to it as a function, because life is just going to be a lot easier that way. Let's call it big F of x. And we're doing this very, very much on purpose, because we know that, actually, you know what, sorry. Let me not do that. I'm getting ahead of myself. We're going to go back to this guy, right? So we're looking at this. We're going to be taking its derivative. But something that we know is that when we use the other part of the fundamental theorem, let's go back to calling this guy b. This is big F of b minus big F of a for any function where big F prime is equal to little f. Okay, so let's do it that way. That'll be probably the easiest way for us to do it. If I take the derivative of this with respect to x, okay, for a moment, you look at it and you say, well, a and b are constants, so I take the derivative, I'm going to get 0. But what if they're not? What if they're variables? What if they're functions? What if they're whatever they want to be? Right? There's nothing to restrict that. If I'm going to take the derivative of the left-hand side with respect to x, then on the right-hand side, I need to take the derivative with respect to x. Okay. What you do to one side of the equation, you must do to the other side of the equation. That's it, nothing fancy. When I take these derivatives, though, I take the derivatives using the chain rule. I can't take the derivative of big F of b with respect to x, but I can take it with respect to b times the derivative of b with respect to x. Right? I'm allowed to do that. That's just using the chain rule. Now, small abuse of notation. If a or b is a constant, then writing something like this is illegal. You can't take the derivative with respect to a constant. But the way in which we kind of sneak around it, I'm not quite done. Let's write this entire thing. The way we sneak around it is that if either a or b is a constant, then I'll be multiplying by the derivative of a constant with respect to x. And that's definitely going to be equal to 0. So as long as I keep that idea in mind, this is going to be an acceptable abuse of notation. We're using something that isn't exactly 100% mathematically kosher. But for the most part, as long as we're clear about what it's doing, we can get to where we're going. Because what this gives us is big F prime of b times b prime minus big F prime of a times a prime, and the derivative of big F is just little f. So it's f of b times b prime minus f of a times a prime. We can use this in general. Don't use this as the conclusion and use that as a way to avoid thinking about it at all. Write out the chain rule each time. Okay? Make sure that it's clear what happens. But once we've got this, it makes our lives pretty easy. Okay? Remember, this is as long as the function is continuous over the entire interval. Okay, if one of these guys, if you're trying to integrate 1 over x, one of these guys is positive and the other one is negative, that's going to blow up. But as long as the function behaves properly and all we're asking it to do is to be continuous, then this thing is going to work out perfectly. So when we go back to a question like what we have above, right, if I have the derivative with respect to x squared minus 4x of the integral from 3 to x squared minus 4x of sine of t squared dt, so I'm looking at just that little portion of it, all I'm doing is I'm saying, well, I'm taking the derivative with respect to box. And what I'm going to get for my result is f evaluated at that box. So it's going to be sine of this box squared. And then if I need to multiply by the derivative of that, then that's just a part of the chain rule. That shows up naturally. Okay? You do this a couple dozen times, it becomes pretty straightforward. All right, so we're going to do things like, what if we wanted to take the derivative of the integral from 3x minus 2 to 5x squared plus x of x to, of t to the 10th minus 3t cubed all to the 5th dt. Right. You want to figure this one out directly, taking the integral, finding the derivative? Go right ahead. Right? But you probably want to get more than full marks on the test, because it's not going to be worth more just because you took the long way around. We've got the derivative of an integral. They're going to cancel out. Right? They don't cancel out perfectly. It's not like with addition and subtraction. Plus 5 minus 5, right back to the same thing. These are significantly more complex operations, and they don't cancel each other out completely because the derivative is not a one-to-one operation. There are multiple things that get sent to the same point. So there are all sorts of little issues. But the idea is still the same. I have two effectively inverse operations. I need to be able to figure out what to do with this. So this is going to be equal to, I think one of the easiest ways to write it is let big F of x be some function such that big F prime, let's go with big F prime of t, that'll make our lives a little bit easier, is equal to t to the 10 minus 3t cubed all to the 5th. Okay, so this is, and this middle step you do not need to write it, but if it helps, then why not? Okay. Then this thing is equal to the derivative with respect to x of big F at 5x squared plus x minus big F at 3x minus 2. There are a lot of instances within mathematics where writing things in the more general way, writing them in terms of the variables, makes things easier than actually writing out the numbers. Right? There's a greater efficiency to it, not to mention the fact that then it applies to everything. So this over here is going to be the derivative of big F at 5x squared plus x with respect to 5x squared plus x times the derivative of 5x squared plus x with respect to x minus the derivative of big F at 3x minus 2 with respect to 3x minus 2 times its derivative with respect to x. Okay? So, what is that equal to? That's big F prime at 5x squared plus x times the derivative of that, which is 10x plus 1, minus big F prime at 3x minus 2 times its derivative. But big F prime, we have it over there, right? It's t to the 10 minus 3t cubed all to the 5th. Ugh. Okay, well, we can write it t is now 5x squared plus x. T to the 10th minus 3t cubed all to the 5th times 10x plus 1 minus 3x minus 2 to the 10 minus 3 times 3x minus 2 cubed all to the 5th times 3. Get practice with it. Find a way to write these up which is comfortable for you and includes all of the necessary information. And it should be okay. Right, there's a great number of ways of writing this thing. They're pretty much all acceptable. Any questions about it? Okay. Let's go over one of the questions from the midterm. This is the one on which the marks were significantly lower than we expected. So it's a useful one to glance at. I mean, obviously, the solutions are there online, but if we look at the function 1 over 10 of arc secant of x. Okay? And the first part of this is we're asked to find out what is the domain of the function. Right? We need to figure things out from the basic components, work our way up. So 10 of arc secant by itself, I don't know what to do with it. But I can look at arc secant. I can figure out what to say about that. Right? Arc secant is the angle which has secant equal to something. Right? Secant is 1 over cos. So what are the possible values that we can have as input for arc secant? Well, cosine goes from -1 to 1. So secant, 1 over cosine, is going to go from +1, it's going to blow up towards infinity. From -1, it's going to go off towards negative infinity. It's not going to hit any of the points inside. So for this over here, for just the inside, what we have is absolute x is greater than or equal to 1. Right, so this is just the first step. This is what is the domain of arc secant. Because if the inside function is not defined, then the outside function is probably not going to be defined either. Now, whatever the result is, can I take tangent of it? Yeah, absolutely. Right? There's no problem with taking tangent of any value. So if we go all the way to this over here, that does not mess around with the domain. The domain is still absolute x is greater than or equal to 1. Where does it blow up? Division by 0. Right? So when I go to the entire function, then I need to look at this and I need to say, okay, well, let me make sure that I'm not dividing by 0. So for what values of x is tan of arc secant of x equal to 0? Okay, so for example, when x is equal to 1, the angle arc secant spits out something between minus pi by 2 and positive pi by 2. Right? So between minus pi by 2 and pi by 2, when x is equal to 1, that's going to give me 0. Right? And sorry, did I say minus pi? I gave the wrong interval. It's from 0 to pi. So when x is equal to 1, arc secant of 1 is equal to 0, tan of 0 is equal to 0. I have to throw that one out. When x is equal to negative 1, I'm going to have arc secant of x is equal to pi. Tangent of pi is equal to 0. That goes away. Now, writing this up is not easy. Right? It takes a bit of time. So you have to actually give your justifications bit by bit, right? So arcsecant of x has domain absolute x is greater than or equal to 1. Tan of arcsecant of x not only has domain absolute x is greater than or equal to 1, we should also look at the ranges. So this one, the range is from 0 to pi, inclusive, minus pi by 2. So you add that bit of detail. Tan of arcsecant has this domain. The range is going to be everything, right? Minus infinity to plus infinity. So I don't really need to worry about that. But 1 over tan of arcsecant of x implies that we need to get rid of 1 over 0. Anything of that form obviously is undefined. So where do we have the denominator is equal to 0? We have tan of arcsecant of x is equal to 0. That implies that x is equal to either 0, sorry, not x, but arcsecant of x is equal to either 0 or pi, which implies that x is equal to plus or minus 1. So those points need to be thrown out. And the domain of the entire thing is going to be absolute x is strictly greater than 1. Okay, but that's the thought process. You look at something and you think, in what ways can it be broken? Right? Where does it work, where does it not? And this is not just for mathematics, this is for engineering. This is in general a good idea. So just a very quick, 30-second example. On my way to my previous class, I went through the lobby at Bayan, and they were handing out quizzes for you to find out whether or not you have a gambling problem. Any of you guys saw those guys? Some of you? Okay, right. So if you think you have a gambling problem, you can fill in this quiz, and they will tell you whether or not you have an issue, and then they will take the quiz, and they put it in a small cardboard box where there will be a draw for a $5,000 scholarship. You got it. If you have a gambling problem that you suspect exists, here's an opportunity to gamble for $5,000. Oh. As engineers, this should really stand out. Okay? All right, have a good day.